Well, think about that. Now, with the uranium tris iodide in hand, you can conveniently convert this into the solvate Phi uranium tris amide, and this material really opened the door to chemistry that is very much transition metal-like. And so here we see a uranium compound in its highest oxidation state, where the highest oxidation state, uranium-6, is not stabilized by an oxo or fluorido ligand. This is a hexachus imido uranium-6 species, and that is a rare example of a TH symmetrical molecule. It's a beautiful molecule. That molecule can be reduced by one electron. You put an electron in the non-bonding FXYZ orbital to generate the monoanion, and this is not a cut and paste error because these two molecules are both the same and are very reminiscent to ferrocene, ferrocenium. You can really swap that electron in and out because it's a non-bonding orbital that is occupying that electron. Now this is uranium-6 and uranium-5. We go down to uranium-4, and from the laboratories of Margaret Jane Crawford at the Technical University of Munich in 2005, this uranium heptakis azido complex was synthesized. By weight, there is more nitrogen in this compound than there is uranium, and everybody who knows about azides probably would expect that this molecule explodes just by looking at it. But frankly speaking, this molecule is just unreactive as the uranium-6 and uranium-5 that I've shown you before. Now we go to the uranium-3 oxidation state. This is a molecule synthesized in the laboratories of McLeverty, Tuckards, Ward, Reingold, and Trofimenko. It's a bis-TP pyrazyl borate ligand. Two of those coordinate to uranium. It's a rare example of an icosahedral N12 coordinated molecule, but although uranium-3 is the most reactive oxidation state in uranium chemistry, this molecule is unreactive. And so all of these molecules that I've shown to you, they are aesthetically quite appreciable, but they don't do any chemistry. And so the reason for that is that pretty much all of these molecules that I've shown to you, they look like snowballs, and even the large uranium center is eventually coordinatively saturated when it is bound to 12 ligands. And so we spend a tremendous amount of time synthesizing tailor-made ligands for small molecule activation. I mean, we need a ligand, a chelating ligand, that stabilizes a uranium center in a reactive oxidation state, but still allows for a small molecule to bind, to get activated, and eventually functionalized. And so we have looked at a variety of ligands that all have the same features. They all have an anchor. In this particular case, the anchor is a 9-membered trisacyclononane, which is a lousy ligand for uranium, but it protects one side of the uranium center. And then the ligand is functionalized with 3 pendant arms, and those 3 pendant arms are here phenols. Those phenols coordinate to the uranium center in this trigonal coordination. Now, most importantly, we introduce steric bulk that is perpendicular to this coordination plane. And the sterically bulky ligand here are elemental functionalities. Now, it doesn't really seem to be a sterically encumbered system, but when you look at the top view and you now look at the space-filling top view, you know that the uranium center is fairly deep buried inside this system. And that actually is probably the most important feature of this presentation. We need steric bulk to protect this molecule, to protect it and prevent bimolecular decomposition reactions, namely dimerization. Okay, so I will point this out one more time. However, this system can still bind small cylindrical molecules such as the carbon dioxide ligand as shown here. Again, the structure looks wide open, but it really is not wide open. The CO2 is tucked into a very tight cavity of 3 elemental substituents. Now, with this system that I just presented to you alone, we managed to actually bind CO2 and activate CO2 by 1 electron. We also could actually lower the steric encumbrance and employ the t-butyl derivative to cleave CO2 to actually form carbon monoxide. We can insert CO2 into uranium element bonds to form amino acids. In principle, we can close a synthetic cycle and eliminate the functionalized CO2 as its amino acid. But of course, I mean, this is a stoichiometric reaction despite the fact that we can close the cycle. We can do multiple bond metathesis. A uranium-5 imido species would react with CO2. The driving force to make this uranium-5 oxo species is tremendous, and then will give you the functionalized cyanate. All this chemistry is actually kind of cute, and when my group accomplished these transformations, every time I was really baffled and astonished. But there are the 2 reactions that we could not accomplish with these molecules. I mean, if you want to activate and transform CO2, all of this would be chemistry that is not expected. Carbonates and oxalates, that was expected, and with these 2 derivatives, we could not accomplish carbonates and oxalates. Only when we introduced a molecule or a group, the neopentyl group, that has steric encumbrance in between t-butyl and elemental, then we could catalytically reduce CO2 to carbon monoxide and carbonate, and we could also form oxalate. Now, at this point, during those years, we started to realize that, yes, the catalytic transformation of carbon dioxide into carbon monoxide and carbonate is a useful reaction, because carbon monoxide could be fed into the Fischer-Tropsch catalysis, but not if you employ like an excess of potassium graphite. You want to use electrons, but those electrons should not come from this tremendously expensive and also a bit dangerous reductants. So here in 2012, 2013, we were talking about and thinking about electrocatalysis. Now, we have learned how to control reactivity by changing groups at this point at the phenol. We have also learned that we can change reactivity by changing the anchor from tricyclononane to a single nitrogen atom. But the anchor is pretty much only there to protect the bottom of the uranium center. Eventually, we also wanted to introduce functionality in the anchor, and we have now employed an arene moiety to actually add more chemistry to it. And so Henry Lapierre was the first, Suzanne Bard was the first to synthesize this particular ligand. And although seemingly trivial, this is a very, very, very difficult synthesis. But eventually we get these ligands, and what we like about the arene-anchored ligands is that they have a set of pi antibonding orbitals. And these pi antibonding orbitals are empty. And when you want to synthesize a low-valent electron-rich metal complex, you can use these these empty pi antibonding orbitals to overlap with my favorite F-element orbital, which is the FXYZ orbital that you have already seen in the introduction. That forms a very efficient delta bond, and this delta bond can then be used to stabilize low-valent species, because you do need electrons to activate stable molecules such as CO2, carbon monoxide, water, H2, and so on. Now, when you look at this delta bond in a very naive way of thinking, and I am actually a naive chemist, I look at molecules, I appreciate them, I look at these orbitals, and I'm thinking that this orbital here would actually allow you to put this molecule on an electrode, and the electrode could then communicate via the delta bond to the uranium center to do chemistry. And so here is the graphical representation. We believe that the delta back bond supports electronic communication between the electrode and the uranium center, and electrocatalysis is what we eventually were aiming for.